Welcome to the deep dive. We're digging into the sources you shared on large reasoning models, specifically looking at their fascinating ability to do what we might call complex, slow thinking, kind of like humans can.
That's right. And these models, they often signal this slow thinking uh, structurally. You'll see explicit pauses sometimes using special tokens like wait before they actually produce the final answer.
But the sources point out a real challenge here. It seems while these LRMs can think slowly, they're not always great at figuring out, when or even how much to slow down.
hmm Which can lead to problems, right? Like getting stuck overthinking something, or maybe just not thinking deeply enough when needed underthinking it.
Yeah, and that feels quite different from how a person might consciously switch gears, maybe based on Kahneman's ideas about fast and slow thinking systems.
Exactly. And people have tried to control this at test time when the model is actually generating. But the existing methods, well, they often seem a bit limited. Well, they might just try to generally increase or decrease the thinking time overall, or perhaps focus only on the computational budget, how many tokens it's allowed to use, kind of blunt instruments.
Okay, so that brings us to the focus of this deep dive then. Your source material introduces a framework called AlphaOne, written as AlphaOne. It's positioned as a more universal way to modulate this reasoning process at test time.
Right. The idea is to get more fine-grained control over both the total thinking budget and, crucially, the scheduling of the slow thinking within that budget.
So our mission today is really to unpack this AlphaOne framework, pull out the key findings from the studies presented, sticking strictly to the source material you provided.
Precisely. Let's get into it.
Okay, maybe you should start with how these LRMs generally approach reasoning according to the sources. It seems like a two-step process.
Yeah, typically it's described as a thinking then answering structure. There's an explicit thinking phase, often using those wait tokens we mentioned to pause and process.
And then it transitions to the answer.
Right. Eventually signaling the end of its thought process with a specific token, usually shown as think, before giving the final output.
But the source highlights that this transition isn't always smooth. The model can do it automatically, but it doesn't always nail the timing or amount of slow thought.
That's the core issue raised. It might generate way too many wait tokens when they're not really helping, or fail to pause and think when it actually needs to, leading to those suboptimal outcomes, overthinking or underthinking.
And you mentioned people try to influence this at test time. The sources talk about things like parallel sampling.
Yes, like generating several possible reasoning paths and answers, and then trying to pick the best one. Best of n sampling is a common example.
Or intervening more directly during the generation.
Right, sequential scaling methods. The source mentions a couple of baselines here. One's called S1, which basically tries to force more slow thinking by just always appending a wait token after certain points.
Okay, just more thinking, basically.
Pretty much. And then there's the other end, like chain of draft or COD, which tries to do the opposite by restricting the thinking budget, trying to make it more concise.
But the sources suggest these have drawbacks.
Yeah, the limitation pointed out is that S1 can sometimes just lead to uncontrolled spiraling thinking that doesn't help, while COD might cut off valuable reasoning too early. It suggests we need something more adaptable.
Which brings us back to AlphaOne at AlphaOne. The sources position this as that more universal modulation framework specifically for test time scaling.
Correct. And it focuses on modulating two specific things.
Which are?
First, the overall budget for the thinking phase, how long it can potentially think. And second, the scheduling of slow thinking within that phase, controlling when it slows down.
Okay, let's break that down. How does AlphaOne actually do this modulation? The source talks about something called the Alpi moment. What's that?
So the ALPA moment is a key concept. It's basically a checkpoint during the generation process. It happens when the number of tokens generated so far hits a specific length.
A specific length determined by?
Determined by a parameter, alpha, which you set. The length is I times the average thinking phase length the base model uses, which the paper calls nthink. So the moment is reached at ith think tokens.
And you set a usually greater than 1?
Typically, yes. Setting a 1 effectively increases the potential budget, allowing for more thinking time compared to the average. But importantly, reaching the item moment doesn't stop the thinking.
Okay. The thinking phase continues after that point.
Exactly. It just marks a threshold.
So that handles scaling the potential budget. What about the scheduling before that I moment? How does it encourage slow thinking then?
Right. So before the item moment, Einta1 actively promotes slow thinking. It does this by strategically inserting that wait token.
Strategically how? Not
Good
just
go.
randomly.
No, not randomly. It tends to append wait after structural delimiters, things like double new lines that often appear naturally in the model's reasoning steps anyway. But the key is when it decides to insert one.
And that follows a plan.
Yes, it follows a user-defined scheduling plan. The source models this as a Bernoulli process. Basically, at each potential insertion point, like after n, there's a probability, let's call it p-weight, of inserting the weight token.
Okay.
But this probability, p-weight, isn't fixed. It changes over time following a specific scheduling function, STT, that the user defines.
So you could, for example, tell it to have a high probability of slowing down early on, and then maybe a lower probability later, like a slow first, then fast strategy.
Precisely that kind of thing. You can define different shapes for how that probability evolves before the end moment.
Okay, makes sense. Then what happens after the on moment? You said thinking continues, but does on do anything then?
Yes, and this is quite important according to the source. After the on moment, AlphaOne needs to deal with what the paper calls slow thinking inertia.
Inertia, meaning it gets stuck thinking slowly.
Kind of, yeah. If the pre-phase successfully encouraged a lot of weight tokens, the model might just keep generating them, struggling to switch back to faster processing or generate that crucial think token to finish the reasoning phase.
So AlphaOne has to nudge it to wrap up.
Exactly. After the error moment, AlphaOne switches tactics. It uses a deterministic method to ensure a transition towards the answer. If the model happens to generate a weight token after the error moment, AlphaOne simply replaces it with the think token.
Ah, so it forces the end of the thinking phase at that point.
Right. It actively stops the slow thinking and pushes the model towards generating the actual answer, preventing it from getting bogged down.
Okay, that's a clear mechanism. Now, the sources detail a lot of experiments with AlphaOne, different model sizes, tasks like math, coding, science. What were the main results? Did it work?
The findings reported are pretty positive, actually. Across the board, different models, different benchmarks, AlphaOne consistently achieved higher problem-solving accuracy compared to the base models without modulation, and also compared to those baseline methods like S1 and COD.
Any specific numbers jump out?
Well, for the smallest model tested, the 1.5 billion parameter one, they reported an average accuracy boost of over 6%, plus 6.15% using Iowa, which is quite significant.
That is a noticeable jump. What about efficiency? You mentioned AlphaOne increases the potential thinking budget, Iowa. Does that mean it uses way more tokens overall?
That's one of the really interesting findings. Despite allowing for potentially more thinking tokens via NUIO, often led to a decrease in the total number of tokens generated compared to the base model.
Fewer tokens overall, even with more thinking. How?
Well, perhaps by making the thinking more effective, it gets to the right answer more directly, avoiding wasted steps, or maybe generating more concise final answer. For that 1.5B model, the source mentioned a 14% reduction in overall tokens on average.
So higher accuracy and potentially fewer tokens. How did it compare efficiency-wise to the other methods, S1 and COD?
Compared to COD, which is designed to cut budgets, AlphaOne did use slightly more tokens on average, about 4.4% more according to the source. But compared to S1, which just adds thinking time, AlphaOne was much more efficient, about 21% more efficient in terms of token usage.
Okay, so it strikes a better balance. They used a specific metric for this trade-off.
Yes, they used the REP metric reasoning efficiency performance. And on most benchmarks, AlphaOne showed a higher REP score, indicating a better combination of accuracy and efficiency.
Got it. Were there any other, maybe more surprising insights from these experiments?
I think one of the biggest ones relates to that scheduling idea we discussed. The experiment strongly suggested that a slow thinking first, then fast thinking schedule consistently performed best for the LRMs.
Slow, then fast. That seems counterintuitive, maybe? Like, you mentioned Kahneman earlier. Humans often think fast first, then slow down if needed.
Exactly. The source explicitly contrasts this with the typical human intuition. It suggests that LRMs might fundamentally benefit from a different approach, one that requires dedicated strategies like AlphaOne provides, rather than just trying to mimic how we think.
Interesting. Any other unexpected findings?
Yes. Another point was about the frequency of inserting those weight tokens. AlphaOne, particularly with its best-performing schedules, ended up inserting weight tokens significantly more often than the baseline S1 method, sometimes over twice as frequently.
So more frequent, but maybe better timed slow thinking prompts were helpful.
It seems that way, yes. Denser, well-scheduled modulation appeared effective.
Let's dig into the analysis a bit more. The sources mentioned ablation studies, taking AlphaOne apart to see which bits matter most. What about those scheduling strategies?
Right. They tested different shapes for that SUG function, the one controlling the probability of inserting weight before the ALA moment. The clear winner, consistently giving the highest accuracy, was a strategy called linear anneal.
And linear anneal implements that slow then fast idea.
Yes, it starts with a high probability of inserting weight, and then linearly decreases that probability over time, pushing towards faster thinking as it approaches the audio moment. Exponential anneal, another slow-to-fast approach, also did okay, but seemed a bit less stable. Strategies that did the opposite, fast then slow, performed worse.
So that really reinforces the slow then fast conclusion for these models.
It strongly supports it, based on this data.
What about varying the ADI parameter itself? Did changing the potential budget scale things as expected?
It did. The study showed that adjusting AW successfully changed the average length of the thinking phase. Larger AW led to longer thinking phases, on average.
But did bigger always mean better results?
No, and that's a key clarification in the source. There's a trade-off. Just making huge doesn't automatically guarantee the best performance. There seems to be an optimal range for depending on the model and task. Finding that sweet spot is important.
Okay. And they also looked at the frequency of weight tokens more directly using a constant schedule?
Yes, using a fixed probability for p-weight throughout the pre-Fezzi phase. This study showed that balance is key. If the probability was extremely low, performance wasn't great. If it was extremely high, performance also suffered.
But within a middle range?
Within a reasonable range, increasing the frequency generally helped, which again points towards the benefit of relatively dense modulation, but not too dense.
Makes sense. And how vital was that final step, the post-modulation, where it replaces weight with think?
According to the ablation study, absolutely crucial. When they removed that deterministic termination step after the ambit, performance dropped significantly.
Why was it so important?
The source explains it using that concept of slow thinking inertia. Basically, the successful pre-modulation, encouraging lots of weight tokens, makes the model likely to just keep generating them. It struggles to break out of that pattern on its own.
So without that forced think, it just keeps thinking slowly and efficiently.
That seems to be the issue. The posty mechanism is necessary to actually achieve the intended combination of slow then fast thinking. It forces the transition needed for the whole strategy to work effectively.
The sources also provided some specific examples, right? Qualitative cases.
They did, yeah, showing AlphaOne applied to individual problems. There were examples where the base model failed, but AlphaOne helped it succeed, like a chemistry problem, a couple of math problems from different benchmarks.
And did it always succeed?
No, they were careful to include examples where AlphaOne still failed, maybe on very difficult math or coding problems.
And what did these examples illustrate overall?
They kind of visually backed up the quantitative findings. You can see in the successful examples how the more frequent insertion of weight tokens seemed to help the model step through the reasoning process more carefully, breaking down the problem in a way that led to the correct solution, consistent with the benefits of the dense scheduled modulation.
Okay, so let's try and wrap this up. The core contribution of AlphaOne, based on your sources, seems to be providing this universal framework for tweaking LRM reasoning at test time.
Right, giving you knobs to control both the overall thinking budget and how slow thinking is scheduled within that budget.
And the evidence presented suggests this approach leads to pretty significant improvements in both problem-solving accuracy and overall efficiency across various complex tasks.
Yes, that's the main takeaway from the empirical results shown in the material. Better performance, often with more efficient token use overall.
So maybe a final thought for you, our listener, to consider drawing directly from these findings. What might that counterintuitive result, the idea that for LRMs, deliberately thinking slowly first, then speeding up, works better than the human-like fast then slow approach suggest about the fundamental ways these models process information compared to how our own minds work? It's certainly food for thought.